This is a video on polar functions and differential calculus. So if you are given a polar function in the form r equals some function of theta, and you wanted to find the derivative of that, you could think of it as dr d theta, and you would just find f prime at theta. If r equals sine theta, then dr d theta would equal cosine theta. And we will do an example in the next video, but for now I'm just going to go through the formulas. So dr d theta in terms of a graph like this would be the rate of change of the radius or the variable r. So if you were looking at this function, as the theta value changes at this point moving along here, it looks to me that the radius is getting just a little bit longer till we maybe get to about here, and then the radius starts to get shorter again. And so right here, dr d theta would be positive. If you were out here, it looks like dr d theta is getting smaller, so dr d theta would be negative if this distance r is getting shorter, and dr d theta would be positive if this distance r is getting longer. And basically you would interpret that as, is the point on the polar function getting closer to the origin or further from the origin as a point moves along this curve? So here it starts getting a little closer to the origin, and then out here it starts getting a little further from the origin. And this is all in terms of theta moving around in this direction, whether the r is getting smaller or larger. And then it often ends up being helpful, just like with parametric equations, to be able to have the x-coordinate of the point. And you already know this formula, x equals r cosine theta. But the x equals r cosine theta that we've been using in the past was when theta and r were specific values, like converting a point. And now we can use this formula for functions. So if x equals r cosine theta and y equals r sine theta, if this were a function situation where r equals f of theta, you would take that f of theta and put it in here. So you end up having some function of theta here multiplied by cosine theta, and that same function of theta here then multiplied by sine theta. And what this will give you then is the x and y coordinates as you move along this green curve. So another name for these functions when you write them in terms of x and y is that they are the parametric form of the polar function. And so then if we have x as a function of theta and y as a function of theta, then we can take the derivative of those. So if you took, say you found dx d theta, which would just be the derivative of the x with the theta being the variable, that would give you the rate of change of the x coordinate with respect to theta. So if we were thinking of it in this example, as we're moving along here, that as theta progresses, the x-coordinate is getting smaller, because right here it's about 2.2, just looking down there, a little bit more than 2. And as the point on the green curve changes here, the x-coordinate is getting smaller. So dx d theta would be negative, all the way until you get to maybe about here. Then dx d theta starts to increase again, because the x-coordinate on these points is going from -2 to -1 to 0 to +1 to +2. Just in terms of x, dx d theta is negative up here, and dx d theta would be positive down here. So of course then there's the companion dy d theta, which would be the rate of change of the y coordinate with respect to theta. And then the same idea, if you are thinking of this function and wondering what dy d theta would mean, if you were right here, think about it, would dy d theta be positive or negative? So dy d theta would be positive because as your point is moving along here, the y coordinate is increasing. And then right after about here, that looks like the y coordinate is going down again. So, well, up all the way to here, and then the y coordinate is going down, 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 down. So until theta gets to about here, the dy d theta would be negative, and now dy d theta would start to get positive again. All right, so dy dx is the last one. Dy dx would equal dy d theta over dx d theta, which would be y prime of theta over x prime of theta. And that is the slope of the tangent line at x comma y, or r comma theta. So what that would mean is you would probably be given a theta value and then be asked to find the slope of the line tangent to the graph at a particular theta value. And you would then find dy d theta, dx d theta, write that as a fraction, substitute in the values, and you would end up getting the slope of the line tangent at whatever point you substitute in. And that would represent the slope of a line, just like it always has. All right, so what's going to happen next? I'm going to create another video for an example of all these formulas. And I just thought I would show you that example quickly so that if you wanted to try it on your own, you could look at this example now and then try it on your own and play the next video to check your results.